Today. Now let me ask you a few questions from your inquiry lab yesterday. All of you, last class period, all of you essentially were studying the same three things, which really were the correct three things that you can study that have significant effect. And one of those was length, different lengths of a pendulum. What were your conclusions? Does the length of a pendulum make a difference in its period?
Yes.
Yeah.
I agree, it does. If I look right here, I have the same mass pendulums. I bring them back to the same angle and I let them go. Oh yeah, they're really, really different. What does shortening the length do to the period? Shortens the period, decreases the time. Yeah, that's exactly what happened. Now, tell me about different masses that are hanging there. So I have two that are the same length. Tell me about different masses. Did they make a difference on your period? Uh-huh. Uh-huh.
Yes.
Uh-huh, uh-huh. I'm getting some of both on this one. Different masses. Did they make a difference? Let's see if we can do. So I'm going to pull it back about the same. If I did it perfect, they don't make a difference.
No way.
They don't make a difference. Now, one thing I noticed, at least one group, and it might have been more, I noticed one group, when they were timing the period, it was often done this way. Go. Stop. Is there perhaps a better way to figure out how long a time to kind of cut down on some error? Anybody have any idea?
During this thing.
Yeah. So I go, and then I let it go maybe 5 times, and then I stop it, and then I divide it by 5. And I got an even better way than that. Instead of saying go and letting go, I'm going to let go and start my timer. And then let it go 5 times. And that's okay. That's okay. I didn't expect you to think of all those things. But those are some of the things that you want to try to think of. How can I cut down on error? There will be error, but how can I cut down on error? How can I make it as good as possible? Mass makes no difference. Now there's another clue to that. I'm holding 22 newtons right here. Let's not hold 22 newtons. Let's hold 22 kilograms right here. And I'm holding 2 kilograms right here. And I'm going to drop them. Which one hit first?
Yeah.
Same. Gravity is accelerating these pendulums. They accelerate at the same rate. It doesn't matter the mass that is going on to them. Now the other thing was how far back you pulled them. What did you find out about how far back you pulled them? Make a difference or not? Pull back farther, period increases? Pretty universal thing? There's one more thing that you did not know yet, that's okay, and that is for these pendulums to function at what we will be learning is called simple harmonic motion, they actually can only be pulled back less than 15 degrees. Now, a lot of you were pulling them back more, and that's no problem because you had no idea about that. That's no problem. But if we keep them under 15 degrees of amplitude, pulled back from the equilibrium position here, then they follow simple harmonic motion, and the distance you pull them back makes absolutely no difference. But when you start pulling them back farther, it does start making a little bit of difference on them, which probably is what you found. So if I pull this one to here, I should have had 2 of them with the same masses, shouldn't I? Yes, sir. Question?
As this is more of a visual class, may I record this on my phone video for those who are not? Like the whole
You feel if you miss some visuals, they are going to miss some visuals, but I think I'm going to pass on that one this time. Thanks. They are going to miss some visuals, but they're going to be okay. Thank you, though, for thinking of that. Let's try this one right over here. So I have them about the same length. So I'm going to pull this one, and I'm going to pull this one right here, and I'm going to try to let them go about the same time.
No way.
Now, it's not the distance they travel, but how much time.
Yeah.
And notice they're both getting to their maximum at the same time. So the amplitude does not matter. As long as I keep it under 15 degrees for a pendulum, the amplitude does not matter. And like I say, you were pulling them much farther back than that because you hadn't studied this chapter yet. And so you probably had a little bit difference in their findings. So, the things that we begin to learn are... What's that? I am recording. You can't see a little red thing because I did the whole board. I don't remember why I did the whole board, because I was probably thinking of pre-calculus that I needed to do show my calculator, but I don't. All right, so it is recorded. Thank you. In a mass spring system. Now, right over here, I have a mass spring system. If, and these two springs are supposed to be basically identical, if I put different masses on them, notice they stretch different amounts. And you could probably figure out if I had a third one, which either a lighter or a heavier mass, it would stretch less or a further amount depending on what it was. The relationship between the force I apply, and gravity's applying the force on this, and how much a spring stretches is called Hooke's law. Now, mass spring systems will also undergo periodic motion, repeat themselves. And you know that if let me just get this one out of the way. If I pull this down and let it up, it just keeps repeating its motion over and over again, right? It has a period. We could time that period. And we could figure out what the things are that affected its period as well. In fact, let's do a little experiment. What do you think? If I change the mass, will it affect the period? Your guess is no. Do you have any reason for your guess?
Oh, wait, what is this? Nah, I'm going to recant this thing.
You're going to recant your statement. So you're deciding a different mass will make a difference.
Are we under procedures?
You don't know. You're not under oath. It's not going to change your grade. What do you think?
No,
we're going to have you vote. We're just having you vote real quick. Everybody vote. Who cares which side you pick? Mass will make a difference in the period. Raise your hand.
Electoral college. Oh, no, really? Oh, no.
Not electoral college. This is popular vote. So 2. Mass will not make a difference. Raise your hand. Some of you are just going with the majority. If you don't vote, then you went with the majority. All right. That's how it happens. So let's just try to count this out a little bit. Now, right now, here's equilibrium. So I'm just going to pull it down that much more than equilibrium. This is a very scientific measure. 1, 2, 3, 4, 5. You got the cadence?
Yeah.
Keep it in your mind. 1, 2, 3, 4, 5, 6, 7, 8. Did it make a difference? These two won't. All right. Besides the mass, and so in this case, a mass makes a difference because it's not just gravity acting a force on it. The spring is acting a force on it. Is why it's being affected differently. What else might affect the period of a mass spring system besides? I have different masses there. The spring itself, how elastic the spring is. You're exactly right. We have something called our spring constant. Have we done that before, spring constant? Okay, so you remember that. Yeah, the spring constant is going to make a difference. So I have another spring in here that happens to have a different spring constant. So let's put it on. And we're going to use this little one. You notice about how far it has stretched? Tell me about the spring constant of this one. Stronger or weaker? Yeah, much weaker. And remember the cadence over here? 1, 2, 3. I didn't count it off, but it's about 1, 2, 3, 4, 5, 6. It's about like that. 1, 2, 3. You bet. Spring constant is going to make a difference in its period. What else might affect it? So far the mass does, the spring constant does. What else might we change? The distance I pull it. So what do you think about that? You have 5 seconds. 4, 3, 2, 1. Will the distance I pull it, we'll call it the amplitude, make a difference? Everybody who thinks it does, raise your hand. Oh, that's the popular one this time. Everybody who doesn't, raise your hand. Okay, well, everybody thinks it does because that was the majority, and if you didn't vote, they're with the majority. So let's go ahead and use this one again. So here's my equilibrium. I'm trying to do the center of mass, so I'm going to pull it this far. Oh, let's pull it this far this time. Pull it that far. So there's my equilibrium. 1, 2, 3, 4, 5. Got it? 1, 2, 3, 4, 5. Doesn't make a difference. Doesn't make a difference. If I pull it too much farther, it just flies off the top, and it doesn't undergo periodic motion. Does not make a difference. So it's kind of interesting to be able to play around with it and see what makes a difference, what doesn't make a difference. Periodic motion is in a mass spring system. They happen to have theirs on one of those frictionless surfaces. I again could not find one of those, so I had to do mine vertically. But the equilibrium position, the position where it naturally rests at, where all forces are equal, so right there's my equilibrium position. So when I pull at a distance, that is going to be my displacement, and that is also called the amplitude. And we're going to use x for that when we run across an equation here in a little bit. So at equilibrium, the spring force and the mass's acceleration become 0. Right there, the net force is 0, acting on it. And my acceleration is 0 right there. How do I know my acceleration is 0?
Going nowhere.
How do I know my acceleration is 0 right there in the middle? Because the force is 0. What does Newton's second law say? Force equals mass times acceleration. The only time I'm going to have acceleration is if I have a net force acting on it. So because I have a net force of 0 right there, there's no acceleration. Does that mean it's not moving? It just means there's no change in its motion. Oh, it's moving, but there's no change in its motion. Where in its motion do you think its biggest acceleration is, which is its biggest change in motion?
When it starts going up,
When it starts going up from the very bottom? Or when it starts going down from the very top? Those are its maximum acceleration points. It is changing the most. And if it's changing the most, it also has the most force acting on it down here. You agree? Yeah. It also has the most force acting on it right up here. Net force. It's mainly gravity there, or it's all gravity there, and it's all the spring there. So theirs is on a horizontal one, so they don't have to worry about gravity on it. Speed reaches its maximum at the equilibrium position. As it goes down, it slows down, 0. Speeds up, fastest, slows down, 0. Speeds up, maximum. So my velocity is at its maximum at the equilibrium position, and it's at 0 at the amplitudes. At maximum displacement, the spring force and the acceleration are at their maximum. And the speed is 0, because it stops right there. It stops up here. Its speed is 0 at those points. Measurements show that the spring force or restoring force is directly proportional to the displacement. All that means is the farther I go from equilibrium, the stronger the force is. Directly proportional. Makes sense? This relationship is known as Hooke's law, and here it is. F, the elastic force, equals negative kx. Negative just means it's the opposite direction. So when I'm pulling it down, the force is up, but I've displaced it down. It's moving in the forces in the opposite direction of that displacement. That's all that negative means. K is the spring constant, and we figured out that different spring constants will have different amounts of force in order to make them move 2 inches. If you have ever had or seen springs that go with an automobile of some sort, and if they were off that automobile, I bet there was no way you could compress or stretch them, no matter how hard you got up and tried to jump on top of them or pull them. Huge spring constant. Guess I better turn the volume up before I attempt to play this.
The spring constant determines how much force a spring will exert for a given compression or expansion. For example, if we attach 1 kilogram weights to each of these springs we see that they stretch different amounts.
Okay, we're done with that one because it's Friday. As we move on, let's look at number 4 on page 367. And I already talked about the spring constant. We're not going to listen to them. And you can read about it if you need more excitement. 367, number 4. So it says, how much force is required to pull a spring 3 centimeters? So we have a displacement that we want to do of 3 centimeters, but we know that, and actually we don't even call it delta x when we're talking about springs, we just call it x. And we know we don't really like centimeters, we like it to be 0.03 meters. And equal in precision, spring constant is 2.7 times 10 to the third newtons per meter. Notice string constants are in newtons per meter, which is why we need our displacement in meters. And they wanted to know how much force is required. I shouldn't even be doing this one for you. This is too easy. So what is our force? Negative of the spring constant, 2.7 times 10 to the third, and then we need to multiply that by how far we have gone, which is 0.03. And tell me about the force.
81.
How much?
81.
81. Now, what does the negative mean? 81 newtons is what the force is. What does the negative mean? Just the direction. Opposite direction of the displacement of that mass. Moving on. It'll be there posted dead photo if I turn the page too soon. So I mentioned that term, simple harmonic motion, when I talked about the pendulum having to be less than 15 degrees. Simple harmonic motion is a motion where the restoring force is directly proportional to the displacement. So in this spring system, it's a simple harmonic motion. The farther away I go, the force is directly proportional to that. On a pendulum, again, and we'll see it later, it is simple harmonic motion, but only when you're less than 15 degrees, because we're working with some angles there. When I pull it sideways, instead of forces directly in the same direction of the motion, our force is different depending how far we pull back a pendulum, so it doesn't continue to be exactly directly proportional. Every simple harmonic motion is a back and forth motion over the same path. Sometimes we just call it SHM, simple harmonic motion. Just goes back and forth over the same path. A pendulum was going back and forth over the same path. So, wonder if we're going to look at these. We'll try.
When an object vibrates or oscillates at a single frequency around an equilibrium point, it is moving in simple harmonic motion.
Look at the force and displacement.
Pendulums with small amplitudes and springs that are not stretched too far often move in simple harmonic motion. The velocity of an object in harmonic motion is 0 at the outer points of its oscillation, where the force on the object reaches its maximum. The object has maximum velocity at the equilibrium point, where the force is 0.
So we said that earlier, something you want to keep in mind. So let's try this one.
An object that oscillates about a point of equilibrium exhibits harmonic motion. The simplest form of harmonic motion is called simple harmonic motion. In simple harmonic motion, position versus time can be plotted by a sine curve. The force exhibited in simple harmonic motion is described by Hooke's law. The restoring force equals negative k times x, where k is the spring constant and x is the displacement of the object. Since the force is doing work on the block's kinetic energy changes with time. Similarly, the elastic potential energy changes with time. However, the total energy of the system is constant. When the block is at its left extreme, the kinetic energy is 0, but the elastic potential energy is at a maximum. The same is true at the right extreme. At the midpoint, the potential energy is 0 because the spring is relaxed. However, the kinetic energy is at a maximum. Because of this, the total energy does not change.
So we continually convert between our different types of energy in simple harmonic motion, but total energy is the same. Kinetic and potential is just varying back and forth, but the total energy is the same because we have those frictionless systems and we don't lose anything. simple pendulum. Simple pendulum is a mass, that's Bob down there, so meet Bob, and it's attached to a string. Any displacement from equilibrium, now equilibrium is right here in the middle where it just hangs straight down. There's equilibrium. Any displacement from equilibrium, the weight of the bob, F sub g, can be resolved into two components. So let's look at this diagram right up here. Gravity is pulling straight down. But I have one force that is along with the string and another force that is going sideways, and it's only that sideways force that moves the pendulum back and forth. This one that's straight against the string doesn't have any effect on it because it's in equilibrium with the string force. So it's only that little sideways force. So as we pull it farther and farther back, well, that sideways force gets larger and larger. So that is why a pendulum, as its displacement gets bigger, so does the restoring force get bigger. And again, as long as we keep it less than about 15 degrees. The x component, that's the sideways force, is the only force acting on the bob in the direction of its motion, and therefore it is its restoring force. The magnitude of the restoring force is gravity times sine of the angle, because it's the opposite side from that angle down there. So we know about that when we're talking about the opposite component. Pre-cal, if it's the y component. All these things go together. When the maximum angle displacement is relatively small, less than 15 degrees, then sine of theta is approximately equal to theta in radians. And then the restoring force is very nearly proportional to the displacement. So that makes it simple harmonic motion. When we keep it small, when we get bigger, it's no longer directly proportional. And so it's really not truly simple harmonic motion. So that's why on a pendulum we have to keep it small. When they say back here a simple pendulum, there are a lot of things that act like pendulums. So in real life, these things that act like pendulums, we model them with a simple pendulum, which has all its mass in the bob, no mass in the string. I mean, obviously there's a little mass in the string, but for our model, we just say, essentially there's no mass here, and all the mass is down here. So we talked about length makes a difference in the pendulum. The longer the pendulum, the longer the period happens to be. Have you ever watched somebody with long legs run compared to somebody with short legs run? And the period of their motion? I know you can visualize the long leg person running and the short leg person running, and they have very different periods of their legs moving. It has a lot to do with this right over here in physics. Restoring force and the simple pendulum. So we talked about it a little bit. Here they're going to draw all these vectors, and I'll let it play in a minute. So notice up here they have the force of gravity in the x direction. They drew it up here at the pendulum bob. It's really down here in my vector addition, my vector sum, that makes the same thing as gravity. But remember, we can move it anywhere we want to. So just keep in mind that it's in the triangle down here at the bottom.
A simple pendulum consists of a mass called the bob hanging from a string. The restoring force in a simple pendulum is due to the force of gravity. If the bob is moved slightly to one side, we can examine that restoring force using a free body diagram. Tension acts on the bob through the string. The force of gravity can be broken into two components. One component exactly opposes the tension. The other is perpendicular to that. This component is the restoring force. When the displacement of the pendulum is very small, its motion approximates a straight line. In addition, for small angles, the restoring force is proportional to the displacement, and the motion of the pendulum is simple harmonic motion.
We're done with that. I thought they had something more profound. Let's look at this chart. That's in your book as well. And really what I want you to concentrate on, this gets fuzzy, the far right side where it talks about the force, the acceleration, and the velocity. So you need to know when I have something in simple harmonic motion and the displacement is at its maximum, that means the restoring force is at its maximum. The acceleration is maximum because force and acceleration are directly proportional to each other. And its velocity is 0. When I am at the equilibrium position, the restoring force is 0, which also means the acceleration is 0. But the velocity is maximum, whatever it happens to be. And then they go to the other side, and it's just like where we begun. But maximum displacement, maximum force, maximum acceleration, 0 velocity. And then they work their way back through it. So really there are two positions, maximum displacement and at the equilibrium. And you need to be aware what is the force, acceleration, and velocity like at each of those positions. Yes, sir?
Could you go back to the 5 seconds?
Could I do what?
The last slide.
To the last slide? It'll be on Edmodo if you need to get to the last slide. So I'll post it so you can go back and look at it. Amplitude, period, I don't have time in the middle of the lecture, no, but it will be there. Amplitude, period, and frequency. Now I've mentioned amplitude. What's amplitude? Displacement from equilibrium. Displacement from equilibrium. I need to know where equilibrium is, and then whatever my displacement, maximum displacement is from that, that is my amplitude. So, a pendulum's amplitude is measured by the angle. So straight down is my equilibrium position, and I can measure how many degrees, or radians would be nicer, but anyhow, I can measure the angle away from that equilibrium position. So my amplitude is going to be measured as an angle in a pendulum. In a mass spring system, well, it's going to be a displacement in a linear measure, so many meters or something like that from my equilibrium position. Now notice the SI units of amplitude are the radian. We covered radian in physics.
Like, at one point, but it was not required.
We did it really, really fast. So let's do a still pretty quick radian thing. If I go all the way around a circle, that's called the circumference. To go all the way around the circle, it's a distance of 2 pi times the radius. If I take the length of the radius and lay it out on the circle, that angle is called 1 radian, and it comes from the word radius. That is 1 radian. So the length of the radius, well, if I go all the way around, there are 2 pi times the radius to go all the way around, or 2 pi radians in a full circle. So halfway around the circle are pi radians, 3.14. Half of that is half a pi radians. 1.5 radians, or 3 pi over 2, so we can just keep dividing up that 2 pi into as many parts as we want. And radian is truly physically related to a circle, so it's a true physical measurement that corresponds to all our formulas. Degrees are just a made-up number. 360 degrees does not relate to any physical aspect of a circle. It's just arbitrary. So that's why degrees don't work in formulas, but radians do. The period, capital T is the period, time it takes for a complete cycle. And we went over for a pendulum. A complete cycle, start on the far left, your far left, swing to the far right, back to the far left. That's one complete cycle. How about the complete cycle in a mass system? What has to happen in a mass spring system? That's what? If, I'm going to start at the easier one, then I'll do the equilibrium one. If I start at my maximum down, a complete cycle has to go all the way to the top and then back to the maximum down. Now, if I start at the equilibrium position, down, up past equilibrium, and then down to equilibrium again, that's one cycle. SI unit is seconds. Periods measured in seconds. Times measured in seconds. We knew that. Frequency, number of cycles per unit time. How many complete cycles do I get per unit time here? That is the frequency of it. And the SI unit for frequency is hertz, after the rental car company. No, not really. So I have cycles per second. If I have 1 cycle per 1 second, that equals 1 hertz. 1 cycle per second is 1 hertz. So 5 hertz is 5 cycles per second. That's pretty fast. It's going to repeat whatever it's doing 5 times in 1 second. So frequency is cycles per second. That's S to the negative first. That means I put that S on the bottom. Period and frequency, here's really our second formula for today, are inversely related. Frequency is the reciprocal of period. Period is the reciprocal of frequency. If I have a frequency of 5 hertz, it means I go 5 cycles every second. And since my period is how long for 1 cycle? Well, if I do 5 of them in a second, how long for 1 cycle? 1/5, the reciprocal of 5. 1/5 of a second is how long it takes for the period. So they are reciprocals, or inverses of each other. We'll try this one, see how productive it is.
Amplitude is defined as a measure of how far the oscillating mass gets from the equilibrium point. Amplitude is measured in radians or meters. Period is the time it takes to execute a complete cycle of motion. Period is measured in seconds. Frequency is the number of cycles or vibrations per unit of time. Frequency is commonly measured in hertz or cycles per second. This pendulum has made 3 complete cycles in a unit of time, so its frequency is 3.
And what is its period if its frequency is 3 hertz? 1/3. 1/3 a second for 1 cycle. They're just reciprocals of each other. So this talks about that relationship over here. Amplitude, we measure it in radians if it is a pendulum, or in meters if it's something that's moving just linearly. Period is measured in seconds. Time it takes for 1 complete cycle, that's called the period. Frequency is measured in hertz, or S to the negative first. Cycles per second. Number of cycles per second is the frequency. So I wonder about a pendulum and what its period is. Here is number 3 formula. This is the formula for how long it takes for a period of a pendulum. The period equals 2 pi. Okay, that's 1 complete cycle, 2 pi. Period equals 2 pi times the square root of its length divided by the acceleration due to gravity. A period's pendulum, even if it physically is identical to another pendulum, is going to be different if you took it to the moon compared to the Earth. Which do you think would be a longer period if I had it on the Earth or if I took it to the moon? The moon is going to be longer, less acceleration due to gravity. So I'd be dividing it by a smaller number down here, and the period of the pendulum would be less when the acceleration due to gravity is less. Yes, ma'am? Length is in meters, and it's going to be the length from its point of rotation up here to the center of mass is where it's going to be. And that is essentially the radius of, if you've made it into a big circle, it's the radius length. It's the length of our pendulum. So let's try 375, number 2.
I hate to ask, but does this mean we can plot wherever the pendulum bob is on a polar graph?
We could. That's right. We certainly could. 375, number 2.
You gotta look pretty.
You are designing a pendulum clock to have a period of 1 second. Did each of you get to that? How long should the pendulum be? Now, you are probably doing it by trial and error, but if I have a nice formula, the period equals 2 pi times the square root of the length divided by the acceleration due to gravity. I guess I'll write it just how they did it right up there. Just a little g is often what we use down there. So what we really are trying to solve for is the length right here. Because they told us what the period was. We know on Earth what the acceleration due to gravity is. So how can we solve for that L? What do I get rid of first? 2 pi. Let's divide by 2 pi. Then, now I'm trying to isolate that L. I got rid of the 2 pi. Then what do? Square. I need to square everything over here. So I got rid of that square root. Now what do I need to do? Multiply by the acceleration due to gravity. So if I did a little more simplified, I'm going to square both of these things. Acceleration due to gravity times the period squared divided by 4 pi squared is going to equal the length of the pendulum that we need. Where did I get 4 and pi squared from? I squared that whole thing. 2 squared, pi squared. So now I should be able to put in my numbers. Gravity is 9.81. The period we want is just 1 second, so I really don't need to worry about that. Divided by 4 pi squared. See if you can do that correctly on your calculator to tell me how long should a pendulum be if you want it to be a clock, where it just ticks off every second. Point, I think we have 3 significant figures. Now it's not 1. This 2 right here is not a data value. It doesn't come in.
Yeah, it's 1.0.
Oh, did it say 1.0?
Yeah,
Oh, 1.0 seconds, that makes it 2. 0.25, is that what you said? There you go. Quarter of a meter, and you have a clock every second. Its period is going to go by.
So do the clock follow that?
So what about these grandfather clocks? Do they follow that thing right there? Well, you do adjust a grandfather clock if it's running fast or slow by a little mechanism that will change the length of its pendulum that is down there. You do adjust it by doing exactly that, the length of that pendulum. Now, grandfather clocks, because there is friction, they wouldn't run forever, right? So grandfather clocks usually have, most of them will have weights on little chains that are using gravity, and they have little gears and a mechanism that helps keep pushing that along, so it helps keeping the time. And then eventually, when those weights get down to the bottom, you have to pull them back up, wind them back up to the top. And that's to overcome friction in the system, is what it is. I love grandfather clocks, but I don't have one. They're kind of expensive.
That's the one.
Mass spring system. Here's our next formula. We had a period for pendulum system. Now, period for mass spring system. I should have gone back to that pendulum system. Remember the things that affect it? The length affects it. And what else affected the period of our pendulum? That was it. Remember, the mass that we put on there didn't make any difference. And also the amplitude, as long as we kept it small, the amplitude made no difference. It's only the length. Now, if I look at the mass spring system, do you remember what affected it? What affected it over here? The mass, the different mass I put on it. Anything else?
The spring constant.
Spring constant affected it. That was over there. How about the amplitude that I pulled it? It didn't. So if we come right over here, I expect to see the mass and the spring constant in the formula, because those are the 2 things that affect it. Very similar formula. 2 pi square root of mass divided by spring constant. 377, number 4. When 2 more people get into the car described in sample problem C, so we have to look across the page to sample problem. I don't know how they decided it was C, but that's the one they're referring to. Probably the 3rd one in there. The total mass of all 4 occupants of the car becomes 255 kilograms. Now what is the period of vibration of the car when it is driven over a pothole in the road? So you've got springs and evidently no shocks on this car, because that's what shocks are designed to do, is to dampen out that oscillation so you don't just go down the road bouncing like this. And by the way, if you're driving a car and you're doing this, you need new shocks. All right. 377, number 4.
Really look at struts.
That's okay. And struts are a combination of the shocks and the spring system. All right, so what do we have? 2 more people get in the car. Total mass of all 4 occupants becomes 255 occupants of the car, 255. So probably we have to go back to the car. It has a mass too, 1275. So we have a mass that is 255 plus 1275. What is that mass? It's okay to use a calculator to add them together. 1530? 1,530 kilograms. All right, so there's our total mass. Car and the passengers. What else do we know about a problem C over here? Mass of the car, combined mass, driven over puddle on the road, frame vibrates, period of... Is it the same period? Now what is the period? No. For the first few vibrates, spring constant. Oh, we have to get the spring constant. So we sample problem 2.00 times 10 to the 4th. Spring constant. 2.00 times 10 to the 4th newtons per meter. So they want to know what is the new period.
Where does number come from?
Came from the sample problem.
Oh,
2 pi square root, help me out, what's that formula for a mass spring system period? Mass divided by spring constant. So really it's just substitute your numbers, use your calculator correctly. What's our mass? 1530. And our spring constant. So now, what is the rate that the car is bouncing up and down at? 5.5 seconds? Anybody else? Yes, no? I'm trying to even find my answer.
Yeah,
They don't think it's that.
yeah,
1.74?
I agree with that. I had too many threes.
1.74 seconds. So our car is bouncing up and down a little slower, so it makes it a little easier to drink your slushy from Stark. All right. I think I am done, and I even have you 15 minutes that you can work on a Friday. So now I can go back to some slides.